Record. Hi everyone. So from today onwards, we will be starting the chapter Linear Transformation and Matrices. So in this chapter, first of all, the very first topic, that is what is a linear transformation? Transformation means actually a function. Function, we always know it is defined from a domain to a codomain. So in this, domain will be V if and codomain U. Now, what type of domain and codomain, what type of sets are V and U in terms of algebra? In this, V and U are vector spaces over field F. Now, we already know what a vector space is. That vector space is defined over a field F, where field has two operations and vector spaces is an additive abelian group with some more scalar multiplication defined with respect to F. So that is what a vector space is. We will be doing it in detail. Apart from that, right now just about linear transformations. F is a linear transformation, F is a function. Transformation means function. Okay, we are done with domain and codomain. Now, why linear? Because F is actually a linear function. What is a linear function? We know that. In general, a linear function means if I have ax plus b, that means a times f of x plus f of b. Actually, f of ax plus f of b. F of ax plus f of b. This is a linear function, right? So same thing over here. First of all, in terms of addition, when we'll be doing it, any two elements from V, f of x plus y, f will be defined over the elements of V, f of x plus y. Linear would mean that it becomes f of x plus f of y. And next thing, vector space. The elements are vectors, and field whose elements are the scalars. How are they interrelated? F of alpha times x. That means alpha belongs to the field F. Alpha is a scalar and x is a vector. Alpha comes out and it becomes alpha f of x. Now these two conditions will mean that F is a linear transformation. How can we combine them into one single condition? Very easy. This becomes f of alpha x plus beta y equal to alpha times f of x plus beta times f of y, where x comma y belong to the vector space V, that's the domain, and alpha comma beta are scalars, they belong to the field. Okay, next thing, if this vector space F is defined over the same domain and codomain is also the same, what do we call it? We call it a linear operator. We call it a linear operator. And we have done this before. What are these two conditions? These two conditions are also called homomorphisms. With respect to group theory, we have done that. So this linear transformation is also called F homomorphism. Because capital F means they are the vector spaces of the domain and codomain are defined over the field F, right? And next thing, if this homomorphism, if this function will be one and onto this homomorphism may turn into will turn actually into isomorphism. Another one more definition, if the function f is defined from V to F, that means V is the vector space and F, this is the vector space over F, and this is the field itself. So this type of linear transformation would be called a linear functional. We'll be doing this in detail at the end. Okay, let's go ahead. Now, one example. What is the most general case of a linear transformation? The most obvious one, we know the function identity function. Identity function. What is an identity function? Identity of x equal to x. This is an identity function. Let us define it over a vector space. Identity function defined over vector space V. We know that if identity function maps every element to itself, so that means domain and codomain are equal. Uh, Such that identity of x is equal to identity x for all x that belongs to V. We have to show that identity of x is a linear operator on V. That's called the identity linear operator. Very easy. Only one condition we need to show. We have already done how to show that whether a function is a linear transformation or not. Alpha x plus beta y, and it should be equal to alpha times f of x plus beta times f of y. So let's just start with alpha x plus beta y. Over here the function is I. So solution will start with, first of all we will have to tell what alpha comma beta belong to the field F, and let x comma y belong to the vector space V. This is V and not U. Okay, so then alpha time x, what will it belong to? Alpha time x, scalar multiplied with a vector. It will belong to vector space V plus beta times y. So see over here, alpha times x, because x belongs to V, y belongs to V. So alpha times x will belong to V. Scalar multiplication, alpha x will also be a element of vector space V. Next, beta times y will also belong to V. And at last, same alpha x plus beta y, two elements of vector space V, V being an additive abelian group. So sum of two elements will also belong to V because of the closure property. So now this is the element that we are considering that belongs to V. So function is actually the identity function over here. So identity of alpha x plus beta y. We have to show this. At last, this should come. Identity means the element itself, alpha x plus beta y. As you can see, it's alpha times f of x. It means x has to be written in terms of the f of x, in terms of the function. And yes, it can be written. X means identity of x. Identity of x plus beta times identity of y. And that is done. Our condition is shown. So this means that I is a linear operator on V. The same thing we can do for a zero transformation. 0 of x, 0 defined from V to V, such that 0 of x, actually this is the vector 0, a function 0, and is equal to 0 for all x that belongs to V. So this is a linear operator on V. Next thing, we will do one more theorem in which we will be doing some results. We have been given let f from V to U be a linear transformation. They are saying then the first part f of 0 is equal to 0, f of 0 is equal to 0. Second part, f of minus x is equal to minus of f of x for all x that belongs to V. And third part is f of x minus y should be equal to f of x minus f of y for all x comma y that belong to V. So we have been just given that f is a linear transformation and we need to prove all of these three. So let's start with the proof of it. Very easy proof. But yes, it's required when you prove big theorems. So we have to show that f of 0 is equal to 0. How can we show this thing? What do we know? We have to use the concept of linear transformations in this. That f of x plus y or alpha x plus beta y, we can split it as f of x plus f of y. This concept is to be used to show this. Let's start with one of the sides. Let's start with LHS of this first part. Left hand side is f of 0. Since I have to use the linear transformation concept, I should have two terms inside the bracket. So, can I write it as f of 0 plus 0? Of course. So linear transformation means that this can be, we can split it as f of 0 plus f of 0. So see now, we have arrived at a situation where f of 0, therefore f of 0 is equal to f of 0 plus f of 0. I know this is obvious thing, but that's how we prove in algebra. Now next step should obey some rule of algebra. What can be done over here? That zero cancellation. When is cancellation allowed? We can either do left cancellation or right cancellation only when we know that it is a group. Now, yes, we know that 0, 0 was an element from domain, and f of 0 is an element from range. F of 0 belongs to range U. And range U, because it is a vector space, with respect to positive, it will be an abelian group. Now, because abelian group, so cancellation laws would exist. And we can always cancel f of 0 and f of 0 either from left or right. It's the same thing in this case. So 0 will be equal to f of 0. So this means that in this vector space concept, f of 0 will always, in this linear transformation concept, will always be equal to 0. Okay? Always. 0 will be mapped to 0 in this. See, 0 will always belong to the vector space. 0 will always belong to V, domain. 0 will always belong to V. Why? Because V is a vector space. And vector space, it means V comma plus is an abelian group. And if it is an abelian group, it means all the 5 properties are satisfied. Out of them, we have identity. What does the identity says? That there is some element that is being added and we get the same element. And we know that this element should be 0. So 0 is the additive identity. 0 will always be present in the vector space. And for that 0, the image inside the another inside the codomain would be f of 0. F of 0. Actually, the value of the image f of 0 would be equal to 0. I'm sorry, not this. The value of the image f of 0 would always be equal to 0. Okay, next thing, f of minus x equal to minus f of x. Same thing. Now, how can we prove? Second part is f of minus x would be equal to minus f of x. How can we prove this? If anytime we get confused, like where to start with, always think from the opposite, from behind, backwards. F of minus x, at last we have to show that this should be equal to minus f of x. That means f of minus x plus f of x has to come equal to 0 in the second last step. So for this step to come, this is a linear transformation. We can combine minus x plus x equal to 0. So this means f of 0 is equal to 0. So this is the thing that we are starting with. F of 0, because f of 0 is equal to 0. We know that. So f of 0 can be written as f of x plus minus x equal to 0. I've just written 0 as x plus minus x, and we can split it as f of x plus f of minus x equal to 0. And from here we got a result that f of minus is equal to minus of f of x. Easy, right? This was an easy way of solving this type of question. Now the last one. In the third part, it is f of x minus y equal to f of, we have to show that f of x minus y is equal to f of x minus f of y. Now this is also very obvious if we treat minus 1 as a scalar in between. And yes, this is what we have to do it like. LHS is f of x minus y. We can write it as f of x plus minus y. Now for the plus relation, the result holds because f is a linear transformation. It will become f of x plus f of minus y. And this is equal to f of x, and f of minus y is actually f of 1 minus 1 multiplied by y. Minus 1 is a scalar, plus in between. So we can write this as f of x plus minus 1 times f of y. So which is actually f of x minus f of y. These were very small things but very important because they bring confusions at the end. Okay, now next important set we will be doing is kernel of a linear transformation and then range. First of all, let's see what is kernel of a linear transformation. We have done a linear transformation f from V to U. Kernel. Kernel is that set, kernel of f, kernel of the linear transformation f. This will be a set. Set of what? It will be a subset of V first of all. It will be a subset of V. And only those elements of x of V, all x that belongs to the domain V, such that they are mapped into 0. They are mapped into 0 of U, such that their images are equal to 0. So this will be called the kernel of a linear transformation. With questions, it would be very easy to that how can we find kernel of a linear transformation? That it will map the elements of the domain into 0 of the range. This is what kernel is. Next comes about the range. The range of a linear transformation or image. Now we know whenever we define a function, there is a domain to codomain involved. What is the difference between codomain and range? This is, if V is domain, then entire U is called codomain. And range is subset of the codomain. Why? Because range consists of only those elements that are images of domain. Images of domain mean f of V. So range of the linear transformation would be set f of V that is equal to f of x. Thus that x belongs to V. That's it. This is called the range, or you say image, and that's it. Okay. These were the two important sets. An important theorem related to this is that we have been given that let f from V to U is a linear transformation. And then we are proving that in the first part we are proving kernel f, about kernel f, and then second part image f. Kernel f, they're saying they both actually is a subspace of, kernel f is a subset of V, so it is a subspace of V. Image f is a subset of U, so it is a subspace of U. Now we know that V and U are vector spaces. How do we prove that whether a set is a subspace of a vector space? Done it before. Subspace is just a subset of that vector space that has the same operation defined. So only there are just two conditions. If satisfied, then we say that a set is a subspace of the vector space. The first one, the set that we are proving to be the subspace, it can't be equal to phi. It's not empty. And the second thing we need to prove is that alpha x plus beta y belongs to kernel phi. Kernel f. Okay, now first implies that we are showing that this set is non-empty. Okay. What does the second one mean? Where we know that alpha x plus beta y, we will be taking elements alpha and b from f and x comma y from kernel f, and we will be showing that alpha times x plus beta times y also belongs to kernel f. What does this mean? Okay, just tell me if x and y, they are belonging to a set kernel f, then will alpha times x and beta times y belong to kernel f? Yes, they will. Okay, if you're confused with kernel f, let's do it with some vector space V. Actually, since we're proving it for kernel f, let's do it for some vector space V, the general one. X comma y are two elements of V. Alpha x plus beta y and beta y separately. Alpha x will belong to V and beta y will also belong to V. Why? Because alpha is from f, scalar, and x and y are vectors. So scalar multiplied by a vector, we know that scalar multiplication, it will belong to V. And next thing, alpha x plus beta y. Addition of two elements from V will also belong to V. Why? Because V, being a vector space, is an additive abelian group. And because it is an additive abelian group, it means closure property is satisfied with respect to addition. So some addition of two elements will also belong to the same vector space. So this means that if we are taking two elements from x comma y, then this type of product and sum, this type of element alpha x plus beta y will also belong to that same set. So first of all, let's see. Over here, we will just be proving that. See, if V is a vector space, then this condition exists. If I have two elements, then the linear combination with the scalars from the field F belongs to V. If V is a vector space, then this thing exists. We are actually proving kernel F is a subspace. Subspace means only one thing, that this set should be a subset of the set. We already know kernel F is a subset of V. And next thing, the operation is same. If we prove this, then that would mean that same operation we have proved. Same operation exists in that set, so that would be a subspace. So that's why we prove this. So let's start with the proof. First of all, we will have to show that kernel F is not equal to phi. How can we prove that kernel F is not equal to phi? It means we have to prove this. Kernel F is not equal to phi. To prove this, we will have to show that there exists some element x that belongs to kernel F. right? If some element will belong to kernel F, that should mean that f of x should be equal to 0, right? And we know that f of 0 is equal to 0. And 0 also belongs to, 0 belongs to kernel F. That will mean this way. We know this. This is the case. So that will mean that 0 belongs to kernel F, that x is actually 0, because this is true. Let's see now. Let's start it. They are saying to prove it, kernel F is a subspace of V. Can we show that 0 belongs to kernel F? For that, we will have to show that 0 belongs to kernel F. If we are showing this, for this, we will have to show that f of 0 is equal to 0, which is actually true. F of 0 is equal to 0 in case of linear transformation, because f is a linear transformation. So our solution, I prove, is very easy for the first part. Because f from V to U is a linear transformation and 0 belongs to V. So 0 belongs to every vector space. So f of 0 is equal to 0. We know that. We have proved that just above. So this would mean that 0 belongs to kernel F. So which implies kernel F is not equal to 5. Okay. Our first thing is proved. Next thing, we have to prove this. We will take this general element alpha x plus beta y belonging to kernel F, and then we will show, actually we will show that, we have to show that alpha x plus beta y belongs to kernel F. We have to show this. In the second part of this, we have to show that alpha x plus beta y belongs. Let's again do it in an opposite way. Now we will be showing at last that alpha x plus beta y belongs to kernel F. Why will alpha x plus beta y belong to kernel F? If f of alpha x plus beta y is equal to 0, then it will belong to kernel F. Why will f of this will be equal to 0? F is a linear transformation. If in before this I write down alpha times, wait, if before this step we get something like alpha times f of x plus beta times f of y equal to 0. So now, is f of, how can we get this? How can we get this? Now this is the point. Something else. What are x and y? For showing this, we always start with, wait, now a little bit how to start. As I wrote, over here, we have to take elements, 2 from field and 2 from kernel F. So we will take let alpha comma beta we will take let, not able to write, yeah, that's fine. Let alpha comma beta belong to F, the field F, and let x comma y belong to F, belong to kernel F. If x comma y belong to kernel F, we know that the mappings, then F would map x to 0, and f of y will also be equal to 0. So now we have to show that, think backward, we have to show that alpha x plus beta y is equal to, belongs to kernel F. This will belong to kernel F. This will be an element of kernel F if f of this element is equal to 0. So let's prove this thing. Let's start with f of alpha x plus beta y equal to 0. We have to prove this thing equal to 0. Let's see what is this equal to. F of alpha times f of x plus beta times f of y, which from above we can see that it would be directly equal to 0. So this means that f of alpha x plus beta y is equal to 0. Alpha x plus beta y is some element of kernel f, is some element that is being mapped to 0. That means it is some element of kernel f. So thus at last we can say that kernel f is a subspace of V. Okay, now in the second part of the theorem we started, it was said to prove that we had to prove that image f is a subspace of U. Now again, those same two conditions. What two conditions are to be proved? First of all, let me see what is given. Given is that f is a linear transformation from V to U, right? F is a linear transformation. And next thing, what is image f? What was image f? Elements of the type f of x, such that x belongs to V. This was image f. Now, in the very first thing, we will have to show that image f is not equal to phi. It's non-empty. Image f is non-empty. Can we know any element? Can we know any f of x that always belongs to image f? Hmm? Can we know any element that always belong to image f? Again, always in such cases, we will think about 0. Image f, if let's say f of x belongs to image f. Again, we already know that 0, if x is equal to 0, x belongs to V. If x belongs to V, f of 0 will belong to f of V. So f of 0 is equal to 0. That belongs to f of V. So in the solution, in the proof, we can start with 0 is equal to f of 0. So this implies that f of 0 would belong to image f, because 0 belongs to image f, so f of 0 also belongs to image f. So image f is not equal to phi. Now, another thing, again, we take two elements from that. Let u1, u2 belong to image f, and alpha 1, alpha 2 belong to f, such that if they will belong to image f, such that we know that if u1 will belong to image f, it would mean that f of u1 u1 belongs to image f. That means f of some element is equal to u1, and f of some element is equal to u2. They are mapped in such ways. Let it be v1, let it be v2. So therefore, okay, this is the reason. Now, again, let's think backwards. We have to show that alpha 1 v1 plus alpha 2, we have to show that we took alpha u1, sorry, alpha 1 u1 was the element, alpha 2 u2 belongs to image f. Why will it belong to image f? If f of some element, if f of some element would be equal to alpha 1 u1 plus alpha 2 u2. So this means that obviously we don't know this element, but we know this. We will have to start with this and express this in terms of f of some element. And that element belongs to the domain, obviously. Okay. Such that this. Now, one more thing, a bit modification. We took two elements belonging to F1, belonging to F, image F, and two elements belonging to capital F, that is the field. Such that, so we didn't write what are V1 and V2. So just telling that whenever we are taking two elements, there are two elements belonging to this image. Two elements, image F, that they are the maps of some elements. There, this means that there exists their pre-images also. So this means, this implies there exist V1, comma V2 that belong to the domain V, such that f of V1 is mapped equal to U1 and f of V2 is mapped equal to U2. We can take it the other way also, that's not a problem. The thing is just we have to prove what is required. So now we will be starting with this thing, RHS alpha 1 U1. So let's see if we are able to write it in the form of some function. So therefore alpha 1 U1 plus alpha 2 U2. What can it be written as? U1 is equal to f of V1. So this can be written as alpha times f of V1 plus alpha 2 times f of V2. Alpha 1 and alpha 2 can go inside. It's a linear transformation. We have done that. Scalar inside or outside doesn't matter. Plus f of alpha 2 V2. Again, linear transformation. We can combine it. This will be equal to alpha 1 V1 plus alpha 2 V2. So see, from here we can see that there exists some alpha 1 V1 plus alpha 2 V2 that belongs to the domain, such that there exists some alpha 1 V1 plus alpha 2 V2 that belongs to V1 and V2 were elements of domain alpha 1 alpha 2 F field. So this will be a linear combination element of V. This element belongs to V such that f of alpha 1 V1 plus alpha 2 V2 is equal to alpha 1 U1 plus alpha 2 U2. So what does this mean? Alpha 1 U1 is the image of some element. So this means alpha 1 U1 plus alpha 2 U2 belongs to image F. That was it. That was it about the theorem. So we have proved both the conditions of a subspace. Hence, image F is a subspace of U. That's it. So now one more thing. The kernel F, we did two types of sets. One was kernel F and the other was image F. Kernel F is also sometimes called the null space. Null space. Never confuse. Null space of F. And image F, it is written as n of null space of F, and image F is called the range space of F. Range space of F, and yes, it is denoted by capital R of F. Another important theorem is about one onto things. We will be asked to prove whether one and onto. First of all, the easiest way how to prove a one function. How do we prove that? Remember, F is 1 if and only if kernel of F only has 0 element. This is how we prove one functions. The easiest way. Same thing over here. What is a non-singular linear transformation? Non-singular means non-singular linear transformation means 1, 1. F is 1, 1, non-singular function. So the theorem says let f from V to U be a linear transformation. Then kernel f is equal to 0 if and only if f is 1, 1. So this theorem can also be stated as, see, one side. In the question, one side we have this kernel f equal to 0 and the other side we have this. So either of these two implies the other. We know that. Another way of writing is a linear transformation f from V to U is non-singular. Non-singular if and only if f is 1, 1. Kernel f equal to 0 actually means non-singular. Okay. So let's prove the first one. Second one is also the same actually. Okay. So let's start. Whenever we have if and only if in between, it means you'll have to prove both the ways. First of all, we'll start with one side and prove the other side, and then we will start with the other side and prove the first one. So first, let us assume that let kernel f be equal to 0. And over here, we will be proving in the end that f is 1, 1. What is the general way of proving that f is 1, 1? Remember, f is 1, 1 means if there are two elements, if there are two elements in the domain x and y, they must be mapped to different elements in the range. They must be mapped to two different elements in range. If by chance these two elements are equal in the range, if f of x is equal to f of y, if f of x is equal to f of y in the codomain, so that will only happen when x is equal to y. This is how we prove 1, 1 function. The same thing we will do over here. We have to prove that f is 1, 1. So let's just start with let f of x be equal to f of y for x comma y belonging to the domain that is V. And we will be using this concept that kernel f is equal to 0 over here. So using that, we will be approaching that because f of x is equal to f of y, then x has to be equal to y. How can kernel f equal to 0 be used? One more thing, we can't directly use it, it's in set form. This means that kernel f, we have to use this thing. Kernel f equal to 0 means there is only 0 inside kernel f. That is, if x belongs to kernel f, 0, 0 belongs to kernel f. If any element belongs to 0, if x belongs to kernel f, if then f of x would be equal to 0. Over here we have two elements involved, x and y both. The trick part of this question, again backwards, think backwards. At last we have to bring this x equal to y. Nothing else can be done, but yes, we can write it as x minus y equal to 0. Right? See now, x is an element of v, y is an element of v, x minus y will also be an element of v. Some element of v is being mapped to 0. What does this mean? This means that x minus y belongs to kernel f. That is, kernel f just has a 0 inside it. If x minus y is an element that belongs to kernel f, it means x minus y must be 0. That's the next step. Okay, if x minus y belongs to kernel f, before that, this would happen if f of x minus y is equal to 0. Okay. Now f of x minus y would be equal to 0 if f of x minus f of y is equal to 0. Linear transformation. F is a linear transformation. Next, this we can take it on the either side and write it as f of x equal to f of y. Now, one important thing I would like to tell you that when we think of how to do the question, we can't do f of x minus y equal to f of 0 and just write it down as x minus y equal to 0 so that x becomes equal to y. This is not possible. See, when we were solving this, I made you solve the opposite way, backwards how we can go. Like just for example, just think if we reach this step that f of x minus y is equal to 0. Now, if I write down as f of x minus y, we know that linear transformation 0 is equal to f of 0 if I write it down as like this. And then I cancel out f and say that x minus y is equal to 0. This is not possible right now, because we are proving that f is 1, 1. We can cancel out and equate the elements. F of x equal to f of y implies x equal to y. We are actually proving x is equal to y from this. This thing is possible only if f is 1, 1. But over here we are proving that f is 1, 1. So we can't use this result. That's why we have to use kernel. Okay. So thus, because of this, we have proved that f is 1, 1. Now, conversely, we will prove it the opposite way. Conversely, let f be 1, 1. Now we can use that result. Let f be 1, 1. Now what we have to prove that? At the end, we have to prove that kernel f only has 0 inside it. So it means we will take a general element in kernel f and show that that element is nothing but 0. Let x belongs to kernel f. If x belongs to kernel f, that means by definition, x is being mapped to 0. If f of x is equal to 0, f of x can be written as f of 0. Now we can use the, because f is 1, 1, because f is 1, 1, so x would be equal to 0, and hence kernel f that we started with equal to x is nothing but just the 0 element inside the set. Okay, done. This was easy, right? So moving ahead with this, let's do a question. Okay, one more thing. Two more definitions, rank and nullity. What is the rank of a linear transformation? Rest of the theorems we would do with questions. Rank of a linear transformation. Again, f is a linear transformation from V to U. F defined from V to U is a linear transformation. Now we will be talking about two things, rank and nullity. See, rank is related to range. Nullity is related to null space. We have just done. Range was image F. Null space was kernel F. Both of these things are related to image and range. And what are these? These are actually the dimensions of those sets. Dimensions. We have done in vector spaces basis and dimension. What is dimension equal to? Dimension is equal to the number of elements in the basis of that respective set. What is the actual definition of rank? We will just be writing it. But what is equal to rank of f? rank of F is actually equal to dimension of image F, range F. Dimension means number of elements in the bases. Bases of image F. So it means there are finite number of elements in the bases. So that means it is finite dimensional V. So let F from V to U is a linear transformation and V be a finite dimensional vector space over F. Then the rank F, which is equal to the dimension of the range of F or the dimension of image of F, whatever you want to write. And one more thing, next nullity. Nullity is also same like this. Linear transformation, V is finite dimensional, nullity is denoted by nu. Nu of F, that would be equal to dimension of, yes, kernel F this time, kernel F. An important theorem that relates these two. We'll be doing the theorems in the next lecture, but that is the rank nullity theorem that relates both of them. That means when F is a linear transformation from vector space V to vector space V and V is finite dimensional. I will also tell that why finite dimensional again and again. And V is finite dimensional. That means rank F plus nullity F is equal to dimension of V. Dimension of V. We will be doing why we talk only about the dimension of the domain and not codomain. Okay. Let's go ahead. We'll be doing the theorem next time. How to prove this. Now V and U are in the theorem we have been given let V and U be finite dimensional vector spaces with dimension V equal to dimension U. Then a linear transformation F from V to U is 1, 1 if and only if F is onto. So can you see this now? Again, we have if and only if in between. One way of doing if and only if is to prove both the ways. To start with one and the other, prove the other and vice versa. But over here, one more way of doing is if and only if means this arrow. If we start with one side and prove all the equations using these two arrows because all the results hold if and only if with this condition, then we can also prove it that way. So this is a very simple and easy way. Let's start with the given with one side. Let's start with the proof with one side that F from V to U is 1, 1. F from V to U we have done if and only if. We have done this, just done. F from V to U is 1, 1 if and only if, yes, kernel of F is equal to 0. We have to prove that F is onto. We know that it is a linear transformation. We know that it is 1, 1. We are just left with to prove that F is onto. What is the way of proving onto? Yes, when we prove that range is equal to codomain. A little bit over here. Range is equal to codomain. What is the range over here? The range is F of V. And what is the codomain? U. So we will have to prove both of these equal. So for proving these equal, if we prove that dimension of F of V equal to dimension of U, yes, Dimensions equal, it means dimension of the range. We have done that. It is equal to rank F equal to dimension of U. Now, if you remember, rank nullity theorem can be used. Rank F plus nullity F is equal to dimension V. That's the range. What is nullity over here? Nullity, let's see. Kernel F is equal to 0. Kernel F only has 0 in it. So that means this is possible if and only if dimension of kernel F is equal to 0, which means nullity F is equal to 0. So nullity F is equal to 0. Now we know that in this side we can write down what happens when nullity F is equal to 0 in the rank nullity theorem. It says that dimension of the domain is equal to rank F plus nullity F. If nullity is equal to 0, then dimension of V will be equal to rank F. So this means that nullity F is equal to 0 if and only if rank F is equal to dimension V. Now over here, how can we bring? See, we are almost done. We just have to bring dimension of V and U into it. F is 1, 1. Because F is 1, 1, we know that, yes, dimension of V will be equal to dimension of U. So over here, we can write this down as dimension of U. Rank F would be equal to dimension of U. Our question is almost solved. Rank F means dimension of range of F is equal to dimension U. So the range, that is F of V, is equal to U. That's it. See, one thing we already know, that the range is a subset of U. That's why we can write directly equal to U instead of doing it both the ways. So hence we can say that F is onto. Hence the proof. Easy. Was it easy? Yes, absolutely. Okay, now some more questions, and then we will be able to understand how can we find the kernel F and the nullity F, and also show whether it is a linear transformation or not. In the first example, they're asking which of the following are following maps F from R square to R square are linear operators. Linear operator means linear transformation where codomain and domain are equal. So that's R square given over here. So let's see, first one is f of x1 comma x2. We know R square will have two tuples, elements of the form x1 comma x2, and it is mapped into R square, that is 2x1 plus 3x2 plus 1 plus 1 comma minus of x1 plus x2. Okay, for it to be a linear operator, linear transformation, we have done one simplest result, that is f of 0 is always equal to 0, right? So over here, according to the element, f of 0 comma 0 should be equal to 0 comma 0. If this is satisfied, only then f can be called a linear transformation. This is also one of the important results. Not always you will have to check that alpha x plus beta y can be opened like that. Okay, let's do it over here. F of 0 comma 0. What would it be equal to? 2 times 0, 0, plus 3 times 0, 0, plus 1, comma, minus 0 plus 0. That is equal to 1, comma 0, which is not equal to 0, comma 0. So this means that this is not a linear transformation. Okay. Second, it's not a linear operator. Second is f of x1, comma x2 given to us as x1 minus x2, comma 0. Now over here, yes, 0, comma 0 will be equal to 0. So we will have to check the other way. Let us take two elements that belong to the domain R square. Let x1, comma x2 first element, and then y1, comma y2 second element. Let them belong to R square, and alpha comma beta belong to, yes, field. R square is a vector space defined over the field R. So how do we do it? Alpha f of alpha times first element, alpha times x1 comma x2 plus beta times second element, that is y1 comma y2. At last we will, you know that what we will show this equal to. Whenever you're confused what to do next, think what we have to show this. We have to show that this thing is equal to alpha times f of x1 comma x2 plus beta times f of y1 comma y2. See, one thing is very much obvious over here, that alpha time of this plus this first element can be written as alpha x1 comma alpha x2 plus beta y1 comma beta y2, right? Then this can be written as f of uh, first element alpha x1 plus beta y1 comma alpha x2 plus beta y2, right? Next, we know that f of what was f of x1 comma x2? Remember abscissa and ordinate. If abscissa is x1, ordinate is x2, then the first term of their image difference of abscissa minus ordinate, and then 0. In the range, abscissa becomes x1 minus x2, and range becomes, ordinate becomes 0. So this should be equal to alpha x1 plus beta y1 minus alpha x2 plus beta y2 first comma 0. This thing, which will be equal to, let's just simplify it, alpha x1 plus beta y1 minus alpha x2 minus beta y2 comma 0. Now if you don't know, if you're stuck what to do over here, it's confusing, let us go think backwards. We have to prove it equal to this thing. This thing means it should be equal to alpha times f of x1 comma x2 would be x1 minus x2 comma 0 plus beta times y1 minus y2 comma 0. So this would be equal to, alpha goes inside, alpha times x1, alpha times x1 minus x2, alpha times 0 is 0, comma 0, plus beta times y1 comma y2 comma 0. Now we can add them. We will add them. This would be alpha x1 minus x2 plus beta times y1 comma y2 comma 0. So we can see that our first term should be this, at the first one, abscissa should be this, and ordinate should be 0. Our ordinate we have got 0, so it means we just need to rearrange the abscissa. When you take out alpha common, and we will be left with x1 minus x2 And beta, if beta taken out common, we will be left with y1 minus y2 comma 0. x1 minus x2 is x1 minus x2 is f of x1 comma x2 plus beta times f of y1 comma y2 comma 0. So what is this thing equal to? We have arrived at, one second, a little bit mistake. What did I do? Alpha times x1 minus x2 comma 0. This was equal to alpha times, yeah, I did a mistake. Let me just erase. What mistake did I do? Before writing into the form of the function, we will have to separate it. We have to separate it in between two. How to separate it? See, this thing is equal to this thing. So we will separate it as alpha x1 minus x2 comma 0 plus beta y1 minus y2 comma 0. So this thing is f of alpha times alpha will come out. One more step. Alpha will come out x1 minus x2 comma 0 plus beta would come out y1 minus y2 comma 0. Now we can write it down as alpha times f of x1 comma x2 plus beta times f of y1 comma y2. And that is it. Since we were doing it for the first time, it was a bit confusing, but trust me, it's very easy once you start solving it by yourself. Okay. Two more things, two final things in this lecture, and the rest we'll do next time. How to find out kernel f and image f when we are given some functions. Let's see an example where we'll be finding kernel f and image f. F is given to us as a function from R cube to R cube. F is a linear transformation defined by f of x1 comma x2, three tuples, R cube x3 is equal to x1 comma, it is defined as, function is defined as x1 plus x2. The second term is mapped to x1 plus x2, and in the third one we get x1 plus x2 plus x3. This is the function given. Okay, we're already given that is a linear transformation, and we will be finding out the function. Kernel f. Easiest way to find out kernel f is let x1 comma x2 comma x3 belong to kernel f. Take a general element, let it belong to kernel f, and then solve it according to the given function and see what is the relation between x1, x2, x3. We will get to know what is kernel f. Okay, if x1, x2, x3 belongs to kernel f, what would it mean? By definition of kernel f, that f of x1 comma x2 comma x3 would be equal to big O, that is 0, 0, 0, 0 vector. So this would be equal to f of x1 comma x2 x3. It's defined as x1 comma x1 plus x2 comma x1 plus x2 plus x3. So big O means 0, 0, 0. This is equal to 0, 0, 0. Now we can equate both the sides. So this implies that x1 is equal to 0 and x1 plus x2 is also equal to 0 and x1 plus x2 plus x3 is also equal to 0. Now it's very easy to solve. If you put this, the first equation in this, x1 plus x2 equal to 0, we would get x2 is also equal to 0. If you have three variables, three equations, just solve them. It's very easy to solve. x2 is also equal to 0. Now x1 is 0, x2 is 0. From here, we will come to know that x3 is also equal to 0. So therefore, x1 comma x2 comma x3 is nothing but 0 0 0. So hence, what's kernel f? Kernel f is equal to only one element, that is 0 0 0. That's it. Now let's talk about image f. Image f over here will be a little different because we can directly write x1 image f over here. We can write it down as x1 comma x1 plus x2 comma x1 plus x2 plus x3 such that x1 comma x2 comma x3 belong to our Q. We can directly write it like this. We will find a basis in the next question given, but over here it was just asked to find out the image f. Okay, one more question. Next question. Let's see what is the next question given. It is given that let f be defined from f of m cross n to f of m cross n. What does this mean? F such that, let's complete it. Let me complete, is a mapping. Be a mapping such that f of a is equal to ab, where what is capital A? Capital A, yes, an element of the domain. It belongs to f of m cross n. And B is a fixed n cross n matrix. X to the power m cross n. What is that? The field of m cross n matrices. So we have to prove that f is a linear transformation and show that kernel f is equal to O if and only if B is invertible. We will understand the question one by one. First, let's prove that it's a linear transformation. Over here, just the difference is we have been given the set of m cross n matrices as a vector space over which f is defined, and the relation is f of a is equal to a into b. Multiplication of two matrices, B is a fixed matrix. How do we prove it a linear transformation? Let two elements belong to the domain f of m cross n, and two field elements, field is f, alpha comma beta, belong to f. Then very easy, then f of alpha times a1 plus beta times a2. What is the relation f of any element is equal to a? That element multiplied by b. So that element alpha a1 plus beta a2 multiplied by b. So this is actually the case of multiplication with matrices. Distributive law is always followed, we know that. This would become alpha times a1 into b. Order has to remain the same. a1b plus beta times a2b. Now, what we have to prove this equal to alpha times f of a1. What is f of a1? a1 into b. This. So this is alpha times f of a1 plus beta times f of a2, because this is f of a2. That's it. So f is a linear transformation. Next, we will start with the second part of the question. They have asked this. Kernel f is equal to, they go if and only if f is invertible. Previously, we have done if and only if f is 1, 1. Now invertible. Invertible means 1, 1 and on to both. We know that. Over here. We will prove the either way. In the first one, Let's start with that B is invertible. Let's start with that. Let B be invertible. Okay, in matrices, what does invertible mean? Invertible means that B inverse exists, and then B into B inverse is equal to B inverse B equal to I. Identity. This is what invertible means. We have to show that kernel F is equal to 0. Pico. The zero matrix. We have to show this. So we will find out, again, same way we have to find out an element. We will take an element, general element of kernel F, and after solving using the given, we will show that that element is nothing but 0. Over here, elements are matrices, so it will be O, the 0 matrix. So in general, let's take an element. Let some element A belong to kernel F. If A belongs to kernel F, that means F of A is equal to O. Over here, it would be O, because range, the codomain is Fm cross n, and 0 of m cross n is O, the 0 matrix. F of A, we know that it is equal to A itself and then B multiplied on the right side equal to post multiplication with the matrix B equal to O. We have to show that A is equal to 0 at the end. We are proving because, right? So that at last we can say that kernel F that we started with that contains 0, it just has that has A, it just has 0 in it. So from here we have to reach here using that B is invertible. Only this thing can be used and we have to reach here. So one thing you can notice that B is removed from here. So that means we can, for removing B, B inverse can be used. We can post multiply with B inverse on both the sides. It would become A, B inverse equal to O into B inverse. And we know that any matrix multiplied with 0 matrix is 0. So that means, and this B into B inverse is A, identity matrix is equal to O. So this means A is equal to 0. Easy, right? So let's start with the converse result now. Conversely, this one is even more easy. Conversely, let kernel F just be equal to O. Now what we have to prove that? B is invertible. B invertible means B inverse exists, right? Okay, if kernel F is equal to 0, both the ways F B inverse exists. We have to prove this thing. So if kernel F is equal to 0, then that means that F of some element of the domain, say A, this will be equal to 0, right? Now we know that. What do we know? When F is a linear transformation, any element, image of element is equal to 0 is possible when that element is equal to 0. We have done that. F of 0 equal to 0. Done it, right? F of A equal to 0 when A is equal to 0, because F of 0 is equal to 0. Or you can write it like, how can we write it? F of A equal to 0. F of A equal to 0. O, big O. F of A equal to F of big O. So 1, 1, because kernel F is just has 0 in it. So it would be 1, 1. We can cancel out FF. A would be equal to big O. We can also write it like this if you don't want to write down directly. So now we have to show that B inverse exists, the existence of B inverse, right? So if A is equal to 0, it means we have to bring A into picture. Right? we will have to bring b into picture, and b will come into picture only if we use the what is given, what is the function. If f of a is equal to o, then a is equal to o, if f of a is equal to 0. So we can also write it that f of a means a multiplied by b is equal to big O, then a is equal to 0. So this thing actually implies this. This is same. This and this, they both are the same. So what does this second line mean? If a b is equal to big O, then a is equal to O. And this would happen only if b is invertible. Why? Why? Because a b equal to 0, a equal to 0. Something happened. A, A, B, B inverse, O, B inverse. A B equal to 0, then A equal to 0. If you multiply something both the sides, only then B would be removed. Inverse of B would be multiplied. Post multiplied with B, only then B would be removed and single A would be equal to 0. So this means that B is invertible. Got it? Easy? It was, I know that. So that was it for today about some theorems and some questions from the chapter. We will continue it next time. Till then, bye and keep practicing.